This conference will now be recorded.
Okay, so today we'll be starting a new chapter, dual nature of radiation and matter. Today actually we'll start with brief introduction of this chapter, what we are going to learn. Then we'll see what is photoelectric effect, electron emission, etc. We'll see, and we'll see the experimental part of photoelectric effect today, and then proper explanation we'll see in the second class. So today is the first class on this chapter. So look, so far what we have learned up to let me check why it is not clear. Is it clear now? Is it clear? Is my voice clear now? Can you message Deepa once again?
Yes, sir.
Is it okay now? Guna madam, is my voice clear to you?
Yes, sir.
Okay, good. Okay, Deepa. Yeah, I have. Okay, good. So, in the last chapter, what we have learned? We have learned like light radiation is an electromagnetic wave. So, till the end of the 19th century, see what all things happen. Maxwell's equations. So Maxwell gave famous equations, 4 equations. So those are the basis of the electromagnetic theory. Okay, so that was actually theoretical understanding, and later on Hart's experiment where he could generate, Heinrich Hertz could generate and detect the electromagnetic wave experimentally. So we could understand that light is an electromagnetic wave so far. And then during the same time, many good things happens. By that time, from the cathode ray discharge tube, X-ray was discovered by Röntgen, and electrons were discovered by J.J. Thomson, and even charge by mass ratio, that is called specific mass of electron, was measured by J.J. Thomson. So why am I saying these things? Because these are related to today's topic, because electron radiation and wave nature of radiation, etc. are little related to our this chapter. Because dual nature of radiation, what is dual? We'll see what is dual. So dual actually is, see, we have seen so far that electrons are, sorry, light is EM wave, electromagnetic wave. So far we have light. Now in this chapter we will see in some cases light also behaves as quantum particle, not classical particle, quantum particle. We have seen in geometrical optics or ray optics, corpuscular model. It is not the same particle model. This is actually quantum particle model. Okay, so light behaves as quantum particle, having energy h into nu. Okay, light is composed of tiny particles which have energy this one. Okay, so in 05, 19, I think 1900 during this time, Max Planck, when he was analyzing the energy spectrum of black body radiation, then he was not able to explain that black body radiation with this wave nature of electromagnetic wave nature of light. And also at the same time, photoelectric effect. Photoelectric effect. We'll see what is that. That was not being able to explain by wave nature. Another experiment is there that is called compound effect. So I'll let you know. There are three experiments. One is black body radiation, black body radiation. Okay. Then photoelectric effect. Photoelectric effect. Okay. Then compound effect. Compound effect. And another aspect is that the hydrogen spectrum or atomic spectrum or atomic spectrum, where energy levels are actually discrete lines.
Ram, voice is not clear, Ram.
Oh, this is not clear, huh?
No, just
My voice is not clear, huh?
your
I
voice
don't
is
know.
not clear. I can't hear you.
I'll check once again. And just a minute, madam. I'll stop the recording.
This conference will now be recorded.
Okay, so today we are starting a new chapter, dual nature of radiation and matter, as I already said. So today, first we'll give the introduction part, as I was discussing that so far we have learned the wave nature of electromagnetic wave. Light wave nature of electromagnetic wave nature of light. Okay, that means light is electromagnetic wave. So these things were actually, see, the electromagnetic wave nature was firmly established by the end of the 19th century from Maxwell's equation and Hertz's experimental proof of that like electromagnetic wave nature of light. Okay, so Maxwell had given 4 equations which are not in the syllabus. So, and Hertz had done very simple but concluding experiment that oscillating charge particle can produce electromagnetic wave and then they can travel in vacuum, okay, in the form of wave. And see, this wave nature of light helped us to explain interference. In the previous chapter we have learned interference, okay, then diffraction, etc., polarization even, okay. But few things in the nature were not being able to explain. What are those? Those are black body radiation. Black body radiation. So the spectrum of black body radiation was not being able to explain by wave nature of light. Okay, then photoelectric effect, photoelectric effect, electric effect. Okay, another experiment is Compton effect. So these are few phenomena. We'll discuss this part today at least. Compton, Compton effect, and another one is atomic spectra. So these four, mainly these four things were not explained by the wave nature of light. If we take the wave nature of radiation, we will not be able to explain these four things, basic things. Okay, so we have seen that ray optics, if we think that light is a classical particle, corpuscular model, that was not able to explain interference, diffraction, etc. Now then Huygens gave the new theory, that is wave theory of light. With that we could explain. Now with the wave theory also we will not be able to explain the spectrum of black body radiation, photoelectric effect, Compton effect, and atomic spectra. Then see, Max Planck in 1900, Max Planck, what he had proposed, proposed that light composed of, okay, light is composed of tiny particles, okay, tiny particles having, each having energy, each having energy h nu. That means these are actually quantized quantity. Quantized in the sense you can quantify, you can express them in terms of integral multiple of this basic unit energy. Okay, so light is composed of quantum particle, not classical particle, quantum particle. So this is the proposition that Max Planck put forward in 1900. Okay, and at the end of this century, 1900, this, like around 1887 or so, X-ray was already explained, like X-ray was discovered by Röntgen. Then electrons, like electrons are particles, right? So those were like discovered by J.J. Thomson, and specific mass of electron, that is E by M ratio, that also was measured by J.J. Thomson. Not only that, around the same time, 1887, it was found that upon irradiating a metal surface with ultraviolet ray, electrons are emitted. And even when a certain material is heated, then also such electrons are emitted. So this is actually called photoelectric effect. When a metal surface, when a metal surface is irradiated with a suitable light, then electrons will be emitted from that particular metal surface. So this effect is called photoelectric effect. We'll read that in detail in this chapter. So the dual nature of radiation and matter, in the sense, see see wave has particle, or sorry, light has light, or radiation, any radiation has either wave or particle nature. They cannot exhibit two nature simultaneously, but they can show either of this wave or particle. At the same time, matter also, since wave can behave as a particle, So de Broglie will be proposing the converse is also true. The particle is a material, like a part of matter. Okay, so part of matter. If wave can behave as a part of matter, a tiny particle, then why not matter can also exhibit wave nature. So this is called wave particle, like this is called wave particle duality or dual nature of radiation or matter. So matter or material particle in motion will exhibit wave nature, or wave will exhibit particle nature in certain cases. Okay, not always. So this is actually called dual nature. Dual nature means wave can exhibit particle nature, even particle can exhibit wave nature. So, but but these, see, if somewhere radiation exhibits wave nature, at that particular situation it will not be exhibiting particle nature. At the same time, if the radiation exhibits particle nature, it will not exhibit the wave nature. So this wave and particle nature, they are actually mutually exclusive. Mutually exclusive. Wave and, so wave and particle nature, wave and particle nature are mutually exclusive. Mutually exclusive. I hope you have understood what is the meaning of dual nature. Exclusive.
Okay.
They are not seen. Yeah. So my voice is clear, isn't it?
Yes, sir, I'm clear, clear.
Guna madam, can you just, yeah,
Yes,
can you just
voice
confirm
is
me?
clear.
Okay, I'll continue
Voice
then.
is clear.
Yes, yeah, thank you madam, I'll continue. So now see, we'll go to this particular effect, photoelectric effect. See, there are 4 experiments which were not explained by the wave nature of radiation. So among them, photoelectric effect will be discussing in this chapter, which is included in your syllabus. Other things you will learn in your higher classes. So to learn photoelectric effect, we need to know few terminologies. So those things we will be learning first. So what is free electrons in metal? See, we have already learned free electrons are there in the metal, right? Free electrons. So what they do in metal, free electrons conduct electricity, even heat, conduct electricity, right? So this is what we have learned in the second or third chapter. Okay. So what do you mean by free electrons? See, in a metal, so whenever I take a piece of metal like that, okay, so there are many atoms, right? There are many atoms, they are closely spaced, right, and very well organized manner, or we can say, you will see in the solid state physics some, when you read in the higher classes, they will be actually arranged in a periodic manner. Anyway, my thing is not that periodic, but whatever it is, there will be many atoms, they are situating very close to each other, and they, like that, that's how they make a solid. If you take a piece of solid, there may be more than 10 to the power 23 or Avogadro number of atoms will be there. Okay, and we know from Bohr's model, somewhat you know, maybe rather for our Bohr's model. So nucleus is there in the, like inside the atom, and electrons are just orbiting around them, just like a planet, like just like planets do in case of solar system. They orbit around the sun, right? So in this case also electrons orbit around the nucleus. And see this, see if I just take that these orbits are circular, so electrons are undergoing a circular motion. For circular motion, the centripetal force is given by electrostatic force, right? Electrostatic force between electron and this nucleus. So nucleus has, suppose, Z into E positive charge. See, Z depends on the proton number or electron number, so this is atomic number, and electron has negative charge like this, okay? And they attract each other, so that is actually providing the centripetal force. Anyway, so what I'm trying to say is that if you take an individual atom, what happens at the farthest orbit, okay, farthest orbit, electron will be pulled very less by the nucleus. So this will be loosely bound electron, or this is called valence electron. This you might have learnt in your chemistry also. So these are called valence electron or nearly free electrons. Okay, free means liberated, but here actually it is not liberated from this atom. This is loosely bound. Loosely bound means what? If you somehow give some energy to this particular electron, it may go out. We'll see in the atomic nuclear chapter. It may go out of this atom. Okay. So when you bring many such atoms here, their outermost electron or the valence electron, they will be actually free from individual atom. Free from individual atom. They will not be bound to their particular host atom or host nucleus. Okay. So they will be free to roam around anywhere like in zigzag motion. Okay. That's how they will collide with each other, with the nucleus or the positive core, etc. Now see, these electrons are freely moving. That doesn't mean that they can come out of the metal surface. Okay, they cannot come out metal surface. Why? Because you take a metal surface which is having net charge 0, suppose net charge 0. That means, so all positive and negative charges are equal in amount, okay, equal in number. So neutral, this metal plate is neutral. Now if one such electron which is freely moving around the metal surface, if it go like if it goes out of the metal surface, then what happens? This become positively charged. This metal surface become positively charged, and then what will happen? Positive and negative, they will attract each other. Okay, they will attract each other, so electron will be attracted by the metal surface again. So it will not be, so consequently electron will not be able to leave the metal surface. Okay, so free electron in metal doesn't mean that electrons can come out of the metal surface anytime or anyhow. It is not the case. Okay, free electrons in the metal means they will be roaming around the, like roaming or freely moving around the bulk or surface of the material, or yeah. So but these are really loosely bound, they don't have much attraction, but some attraction will be there. Some forces will be applied, okay, by the rest of the cores of this cores of the atom. So anyway, so if you want to take any electron out from the metal surface, you have to provide certain energy by which it can overcome this pull, okay, or it can be free from the pull. See, when it is trying to come out from the metal surface, then positive cores, they are attracting towards the metal surface. That's why it is not able to come out of the metal surface. But if you give some energy this to this electron such that it can overcome this pull and come back. So I'll just give you a simple example. Suppose you are you are participating uh, like tag of wire. So there are, see, there are 5 friends this side and this side 5 friends. So if they are actually pulling each other with equal force, then nobody is going to win, right? So if some party has 6 people, they have extra force, so they can pull you there. Okay. Similarly, if you have a metal surface and if you want to take one electron out, you supply some energy to this electron so that it can overcome the pull by positive force of the metal. So you need to give some minimum energy, okay, certain minimum energy for a particular material. So that is, so the minimum energy you supply to that electron to come out of or overcome the pull of the metal surface and come out, that minimum energy is called work function. So what you have to provide to an electron to come out of the metal surface is called work function. So this is what, this is actually minimum energy. The I'll write down what is that. The minimum amount of energy. Minimum amount of energy minimum amount of energy required by an electron to just escape to just escape from the metal surface is called work function. Is called work function. This is called a work function. This is certain energy, and it is actually denoted by electron volt. Okay, so this energy is denoted by, sorry, this energy is denoted by phi 0, denoted by phi 0. Some cases you will see W or W0. Okay, this is the notation of work function. Notation in your ncert textbook, it is phi 0. Notation of work function, I am just writing as short notation W of work function. Okay, and it is measured, it has a unit. Actually, work function has unit. I write work function that has unit electron volt. Electron volt. Electron volt. What is electron volt? 1 electron volt is, if an electron is accelerated through a potential difference of 1 volt, then the energy, kinetic energy, you can say kinetic energy gained by electron is gained by the electron is called called 1 electron volt. Okay, so if an electron is accelerated from rest, actually, okay, accelerated from rest through a potential difference of 1 volt, then the kinetic energy gained by the electron is called 1 electron volt. And see, 1 electron volt, then what, 1 electron volt is equal to 1 electron. See, this is the electron and this is the voltage, 1 volt. So 1 electronic charge is 1.6 into 10 to the power minus 19 joule, sorry, minus 19 coulomb. Okay, and along with that, so coulomb, this is coulomb into 1 volt. That means coulomb into volt means joule. You know, this is Q into V is equal to work done, right? So work done has unit joule, so it will be C into V is joule. So 1.6 into 10 to the power minus 19 coulomb into volt means this is joule. Okay, So this much joule, 1 electron volt is this much joule. So this is the smallest unit, and in atomic physics we'll be using this. And if you go for nuclear physics, this will be written as 10 to the power 6 of this. Okay, 1 ev into 10 to the power 6, that is mega electron volt. Okay, MeV. Then if you multiply 9, 10 to the power 9, then it will be giga electron volt. Okay, like that. So these are actually for nuclear and particle physics, high energy physics, and electron volt energy we use for low energy physics or solid state physics or atomic physics. Okay, so work function will be denoted by, measured by the unit electron volt, and it is denoted by phi 0. Okay, the minimum energy required for an electron to escape from the metal surface. Okay, so yeah, now let us see electron emission. Okay, I have already talked about this electron emission. See, when an electron escape from metal surface, that is called emission of electron. Okay, so this is called emission of electron. So we have seen that for emission of electron you need to provide that particular energy, that is work function amount of energy, at least minimum that energy you have to find, you have to give to the electron. Okay, so if I ask you that how many ways are there to provide provide this work function to electron so as that electron come out of the metal surface or electron emission happens, there are many ways. One is actually thermionic emission. Okay, thermionic emission. Okay, thermionic emission means you take a metal surface and then heat it. Okay, heat it so that electron gets sufficient energy from this heat. From that heat itself it will acquire energy to come out of this metal surface. Okay, so you know this heat actually gives the kinetic energy to electrons. Okay, temperature, like if you heat it, heat energy will actually increase the temperature of the particular metal surface, and electrons, their kinetic energy will be increased, and that's how they will be overcoming this work function amount of energy. Okay, this is thermionic emission. Then if you apply a high voltage, so this is called field emission. So next is field emission. Field emission means what? If you apply a very high voltage, okay, very high voltage, across the metal surface, then also electrons will be very high voltage means how much? Of the order of 10 to the power this much. Okay, sorry, volt, 10 to the power 8 or 10 to the, more than, at least more than 10 to the power 6. If you apply, then volt. Okay, so electric field, if you apply very high potential difference across the metal surface, then electrons will come out from the metal surface, and this is called field emission. Field emission. Okay, field emission. And the last one, that is the one which we are going to discuss today, is photoelectric emission. Photoelectric emission. What is this? So anyhow you have to provide energy to the electron on the surface. So suppose if you irradiate the metal surface with some suitable radiation or some suitable light, mainly ultraviolet, okay, ultraviolet ray, etc. Then what happen? This electron will gain energy and overcome the work function. Okay, overcome this work function of the metal surface and come out of the metal surface. So this is called photoelectric emission. What is, see, this name has very good combination, photoelectric emission. So this is a suitable name for this emission, photoelectric emission. So if you incident some photon, then electrons are emitted. So this is called photoelectric emission. So this phenomenon is called photoelectric emission. So I'll just write what is photoelectric emission then. So the phenomenon of emission of electrons from the metal surface, from a metal surface when a light or radiation of suitable frequency. I'll let you know what is suitable frequency, why suitable frequency. Okay, suitable frequency is incident on the metal surface is called photoelectric emission or photoelectric effect. Photoelectric effect or photoelectric emission. Okay, photoelectric emission. And see why photoelectric, because we are shining light or photon, and then we are getting electron out. Okay, emission of electron we are getting. See, suitable, why I said, because see, I have various kind of materials. See, the work function I told, work function which is phi 0 we have denoted. So this work function is not same for all the materials. I have various metals. So all the metals do not have the same work function. It depends on how much the attractive force is there, right? So that depends on the structure. In fact, it depends on the material. It varies material to material and also the surface. If some surface is very shiny, then electrons are ready to come out, okay, with minimal energy supplied to it. But if very rough or something like that, then you need to supply more energy. Anyway, so you just remember that this work function actually varies metal to metal. So that's why a suitable energy has to be given. Suitable frequency means suitable energy, like light has to have suitable energy so that it can see the energy. Okay, energy of the photon has to be, or light has to be greater or equals to, at least equals to or greater than the work function. Okay, so each and every material or metal cannot be showing photoelectric effect with the same light. You have to, some cases you have to take ultraviolet, some cases you have to take X-ray. Okay, so various radiations you may have to take. Okay, because this work function, because of this work function is not same for all the metals. Okay, so the phenomenon of emission of electrons from a metal surface when a light or radiation of suitable frequency is incident on the metal surface is called the photoelectric effect or photoelectric emission. Now the electrons which are emitted is called, actually they are called photoelectrons. The electrons which are emitted, they are called photoelectrons. Now look, what I'll just do one thing. See, I have a metal surface now. Okay, so I am shining with light, okay, with some radiation. Then see, electrons are coming out. Okay, if I can make a circuit such that the electrons are flowing through the circuit. Okay, if these electrons which are emitted by the metal surface, if they are made to flow in a circuit, then what I get is current. So this current is called photo current. Okay, photo current. If we can make these electrons, emitted electrons, to flow in a particular circuit, what we get is called current, because flow of electron is current or flow of charge is current. So this current, what we get is called photocurrent. So basically, experimentally, when we will be verifying this photoelectric effect, we will be measuring the photocurrent with respect to various factors. With respect to various factors. So what we have learned here, see, we have learned few things, few terms: work function, that is the minimum energy required for an electron to escape the metal surface. So that is, work function means that is an energy denoted by phi 0, and it is measured with electron volt unit. Then the the photoelectric effect, we have learned what is photoelectric effect. I'm just summarizing whatever we have learned so far. Photoelectric effect or photoelectric emission. Okay, and the electrons which are coming out or emitted from the metal surface are called photoelectrons. Photoelectrons, electrons, electrons. And the current we get out of these photoelectrons are called photocurrents. Okay, these are the terms we should be familiar with before we go to the deeper in this subject. Okay, so now we'll see the photoelectric emission was first observed by Heinrich Hertz. So we'll just briefly discuss the Hertz experiment, and then we'll stop it today. So because it is already going to 7 o'clock, I'll just take another 10 minutes. Then I'll stop for today. Tomorrow onwards, we'll just see, like, not tomorrow, next class, we'll see the experimental, like, experiments. Various experiments were done on photoelectric effect, where photoelectric current were measured with respect to intensity of the light, with respect to frequency of the light, with respect to changing in the potential. We'll see that. So those things are there. So for today, what we'll do, we'll just discuss the first experiment where the photoelectric emission was guessed to be happening, or like proposed that there is such kind of things happening when you shine a metal surface with light. So that was actually Hendrik Hertz who had actually proposed first this photoelectric emission. But anyway, at that time it was not known photoelectric emission. Later on, Halwachs and Halwachs and another scientist, I'm forgetting his name. Just a minute. Okay, so yeah, Halwachs and Linards and Linard and Halwachs, they had carried out a detailed experiment on photoelectric effect, which we'll be discussing on the next class. So today we'll just stop with this Hart's experiment. So what let me just tell you this brief history of this experiment little bit. So see, by this time Maxwell proposed, what Maxwell proposed, that EM wave actually travels from one point to another. It travels from one point to another. Okay, and see, electromagnetic wave can be produced. See, production production can be done from oscillating charge. Okay, oscillating charges. And another basic point was EM wave travels in free space. Travels, basically, light we have seen travels in free space. Okay, doesn't require any medium. So that is what I want to mean by free space. So these two things actually were verified by Heinrich Hertz by this simple experiment. So Maxwell had already proposed that oscillating charge particle can produce electromagnetic wave and it can travel through a vacuum. Okay, it doesn't require any medium. So these were two facts which Henry Hertz was verifying. How? See, this is a battery and there are two coils, you can see that. So this one and this is another one. So these are actually called induction coil. By induction coil, you can produce a high electric field. So just to produce very high electric field or potential difference, produce high field, high field. How? It is due to induction. See, this is a battery. If you change, see, this is actually switch. If you just like very quickly, if you just switch on and switch off, then there will be change in the current in the circuit or through this coil. An inductor coil, if current is varying, so there will be induction EMF will be induced d, you see, L di dt, right? L di dt. Okay, like that. So you can induce a very high field with this induction coil. So see, with this induction coil, there are two things. These are actually metal plates. Okay, metal plates, metal, simple metal plates, and these metal plates are connected to this induction coil with thick copper wire. See, this is thick copper wire, thick copper wire. Okay, thick copper wire. This also thick copper wire, and at the end of this copper wire, you look, these are denoted by S. I'll just clean everything. So see, these are actually metal sphere, metal sphere. These are actually metal plates. These are no, see, these are denoted by C because the cathode, they can emit electrons. Okay, or these are called emitter plates, metals, metal plates. Okay, metal plates. So these two are called even cathode also, or emitter plate. Okay, cathode. And see, these two are spheres, as I said, and there is a very small gap between these spheres. Okay, very small air gap is there. What is that? Air gap. Very small air gap. And is, if you know this thing, that if you have two metal, okay, metal electrodes like this with a very narrow, air gap, and if you can produce a very high field across this gap, high field in the sense, at least it has to be greater than 10 to the power of the order of 10 to the power 6. If you can produce that much of field, so this actually will be exceeding the breakdown voltage of the air molecules. Breakdown voltage of air molecules. What is breakdown? See, generally what happens, see, there, if there is a gap, then there will be no conduction through this gap, right? No conduction through this gap. But what happens if you produce a very high field, which is of the order or maybe greater than 10 to the power 6 volt, then what will happen? This volt will actually, this much, see, there will be very high electric field. So air molecules here will be ionized. Okay, air molecules will be ionized. Air will be ionized. So if ionized means what? So air molecules generally, they are neutral, but they will be creating either positive or negative ions. So see, positive and negative ions. So what they will do? See, this positive and negative ions, they will give a nice path for electron to go from here to here, and this will actually produce a spark. This will produce a spark. What it will produce? A spark will be produced at this small air gap. So this is what is done here also in this experiment. So look, these are the metal spheres, and between these metal spheres a very narrow air gap is there, and by this induction coil a very large very large amount of electric field is produced across this air gap, okay, on this spheres. Very large electric field will be produced. Then there will be a spark produced, okay, spark produced, okay. So if the spark is produced, spark means what? Some kind of radiation, right? Light, some kind of light. So that is electromagnetic wave. So this is how spark was produced. And see, these two plates were actually acting as capacitor plate, okay. They can actually holding the charge on both sides. So what was happening? A very large electric field was produced here by this induction coil, and because of that there will be a spark generated and electrons will flow, like they can flow through this gap, okay. So this spark, see this spark, as soon as you see this spark over here, at the same time hearts could see spark in this coil also. I have not explained about this coil. See, this is a ring. This is a ring, metal ring with small sphere over here with a small narrow air gap here. Very narrow air gap. So this is actually acting as receiver. So these are acting as emitter. This is acting as emitter, and this is actually receiver or detector. So we have seen that emission of electromagnetic wave is happening here, and see, Harj actually was thinking that if the spark is generated here, okay, then it has to travel up to here to produce or generate a spark over here. Because see, if there is a very high voltage, and see, by spark, if the ions are coming and like see electromagnetic wave that is also having electric field and magnetic field, you know that electromagnetic wave is combination of electric and magnetic field. So if they reach over here, there will be a huge like electric field produced across this gap also. Then here also you should see some spark, okay. See, if truly, if Maxwell's proposition is, or his proposal is true, that electromagnetic wave can travel through vacuum, then what happens if spark is produced here, okay. So at the same time immediately spark should be produced at this receiver also. In fact, it was seen. So when the switch is on, when the spark is seen here, at the same time he could see some spark over here. You can see in YouTube there are many experiments, Harsh experiments demonstrations. You can look this videos so that you can understand what I'm trying to say. So what is that? Whenever you switch on and switch off this, so there will be huge potential difference across these two surface like spheres, mental spheres, and hence the air molecules in between this air gap will be ionized and electrons will pass from here to here, and there will be a spark generated. So that spark will be traveling all the way up to here to this receiver ring, and here also there are two spheres, and as soon as they come, there is, see, electromagnetic wave means it has electric and magnetic field both. So electric field will produce high electric field will be produced across this also, and hence there will be a spark simultaneously. You can see spark simultaneously here and here also, okay, in the receiver ring. So then with this actually he could explain the production and the propagation of electromagnetic wave. But what is very much related to photoelectric effect is here is that, so what he was doing, what Harsh was was doing, he was actually shining light, okay, to this emitter plates, okay, shining light with, sorry, shining these emitter plates with some radiation, some ultraviolet ray to this emitter plates or cathodes. These are called cathodes or emitter plates. They were shined with some some radiation, and upon shining that, what is seen is that this high voltage spark is actually, so what was seen earlier, like without any radiation, it was smaller in extent, but when it was shined with some radiation, these two emitter plates, then he could observe that more spark is generated in the receiver. More spark is generated in the receiver. Okay, more spark is generated in the receiver. So what he concluded is that, see, this electromagnetic wave was created by the oscillation of electrons in this gap. Okay, oscillation of electrons in this gap, or acceleration of electrons during, like in this gap. So which is producing electromagnetic wave, and that is traveling through vacuum, as Maxwell proposed. Electromagnetic wave travels in vacuum. That was proved. Production was proved due to oscillation of electrons. Now why the spark was increasing when you shine with this, like shine this metal plates with ultraviolet ray? That is because when you shine these emitter plates, somehow some electrons which are generated or coming out of the metal surface, they are coming through this, they are actually passing through this gap. Okay, that's how more electromagnetic wave is generated here, and spark also is increased in this receiver coil. Okay, so this is how Hertz actually had proposed, or he actually guessed this upon shining light, maybe electrons are generated, okay, from the metal surface. Electrons are emitted from the metal surface. Because of that, this spark is actually increasing. So this is the first and very primitive experiment in Hertz experiment, like very primitive experiment on photoelectric effect. Okay, then thereafter we'll see the experimental, like proper experimental arrangement of photoelectric effect, and we'll see various effect like intensity effect, then potential effect, then frequency effect, and many other things, and we'll try to explain why this particular variation of the photoelectric current is like current is there out of this, like with these various factors. Okay, how photoelectric current is varying with various factors like intensity, frequency of the light, and the potential applied across the collector and emitter plate. We'll just explain this experimental arrangement, as well as we'll explain various experiment, like various observations, and how electromagnetic wave was, like wave theory was unable to explain, but quantum particle theory, or particle nature of electromagnetic radiation can explain this photoelectric effect. We'll discuss in the next class. Okay, so thank you for your patience. If you have any query, question, or doubt, you can ask me, Deepa, or otherwise I'll stop. You have any question, Deepa? I'm not getting your response. You can write in the chat box. Okay, then I'll stop it here. So bye for today.